So the name of the session that you have for us here is the future of .NET in real-time 3D applications with Unity. That sounds like a lot going on there.
Yeah.
I'm looking forward to seeing what we could do with this. I know some folks have talked about doing some cool things with Unity in 3D space using perhaps some of the Meta Quest devices. So I'm interested to see a little bit more about what you've got here for us.
Yeah, thank you. We're gonna dive deep. Yeah, we've got a lot of content. I mean, so for those who don't know me, I'm Josh. I lead the .NET VM team at Unity, and we're part of the .NET Tech Group. And our kind of goal is to really make the developer experience with Unity a great one. So I'm really excited to kind of share some of the details about the amazing things you can use .NET to do to deliver these really great real-time 3D experiences with Unity. You know, some of you watching might be, a seasoned Unity developer. You might be using .NET Game Dev with another engine, like JB mentioned, or you might be just looking to start game development with .NET. And no matter what your use case is, Unity's got some great tools to help you bring your ideas to life. So today we're going to kind of tell a story of C# and .NET at Unity. We're going to look at the past and the present and the future. Take a look at some amazing compiler technology we've developed. We're going to alternate between some high-level strategy, some low-level deep dives. We'll do a bit of live coding and see how it goes. So yeah, let's go and get started. So what is it that Unity provides to developers, to .NET developers? Well, we like to think of it in terms of these three pillars. We've got C# tooling for your game scripts. We've got a .NET runtime that works across all the platforms Unity supports. And we've got the Unity runtime, which is really a focused set of APIs to deliver real-time 3D content. And like JB mentioned, Unity's been around for a while, right? Almost 20 years now. So this didn't just kind of show up immediately. This has kind of evolved. So I want to give first kind of a background of the history of what happened. So starting back on the left there in 2006 is where our timeline starts. On the top, you can see kind of .NET's development over the past 15 or so years. And then the bottom is Unity's kind of history and progress, where we've gone with Unity. And I really want to call focus to kind of the last 7 years or so. Since the .NET ecosystem became more open source, Unity has continuously invested in improving our .NET integration. Now today, like JB said, Unity supports C#9 and .NET Standard 2.1. We use a number of different technologies behind the scenes. Mono, we use as our just-in-time or JIT runtime solution on desktop platforms. We use an in-house VM called IL to CPP for ahead-of-time compilation on these ALT platforms like mobiles and consoles. And we have this pretty cool compiler called Burst we use for high-performance code. We're going to kind of talk about each of those a little more in-depth as we go through today. But there's a lot here, a lot of history at Unity. So I want to kind of start off now with a bit of a step back. Let's look at a high-level overview. If you're new to Unity, how does it actually work? How do we get from C# code in Unity that you write all the way down to code running on a target device? So we start off with the C# code. It might be game scripts. JB had mentioned Unity's got this great package ecosystem of C# code out there. And a lot of the Uni engine code actually is written in C#. And we use the Roslyn C# compiler. And that, of course, gives us .NET assemblies, right? The IL bytecode that we're going to execute. And from there, we can kind of branch out to different options. So we've got Mono, which is the just-in-time runtime. We use that on Mac, Windows, Linux desktops. IL to CPP is this in-house VM that we developed for the ahead-of-time compilation. Like I said, mobiles, consoles, web even. And then there's Burst. Burst is for high-performance code. It can actually run with Mono or IL to CPP in either a JIT or an AOT mode. That's pretty cool. But the bottom line is we start with your C# code. You're building your game scripts, building the logic for your game. And at the end, we're running across lots of different devices, whether it's, x86, ARM, mobile console. If there's a place you can play a game, Unity probably supports it. Well, one of the cool things I like about working at Unity, though, is kind of the culture of the company. And really, feedback is important. We love to solicit feedback. So we always want to ask the question, what are our users, C# developers, .NET developers using Unity, what are they asking us? Well, first of all, users of Unity want access to the latest C# language features, right? Things like default interface methods and faster string interpolation. We recently shipped full support for C#8. We're now shipping support for C#9 language features. Users want access to NuGet, right? There's lots of great high-quality package and solutions out there. And right now, to use NuGet in Unity, it's pretty difficult. We're going to try to fix that. Users want fast code iteration, right? We want to build code, in Unity just as fast as we can in Visual Studio. Users want the best tools, right? We want to be debugging, profiling with all the latest tech. Of course, .NET 7 was just released. Unity is using .NET Framework 4.8. There's better runtime technology out there. The GC and the JIT of Core CLR are really efficient. We're going to talk about those a bit later. Users want access to those in Unity. And finally, Unity's got this really excellent API, but it doesn't actually fit with a lot of standard .NET APIs. Things like async await don't work really well. Users want advanced networking APIs in Unity for multiplayer games and efficient data management by things like Span and Friends. So, these are all the things we're hearing from our users, and it's one thing to hear them, but this has got to be followed by some action. So, what's the future strategy for C# and .NET Unity? And if I could sum it up in one sentence, it's this: Unity should provide the best developer experience in the .NET ecosystem. That's what we're aiming for. And we're going to try to do this by focusing on really 3 areas of strategy. The first one is consolidation. We need to get things inside our own house in order to prepare us to build upon the .NET world. And then second, we're going to look to standardize, modernize, and innovate. There's lots of great technology out there on .NET. We need to bring that to all of our Unity users. And finally, and probably most importantly, we need to improve communication and collaboration. .NET's got a great open source ecosystem. We want to fully engage with that ecosystem at Unity. Well, I want to dive a little deeper on each of these strategy areas. We're not going to talk about the consolidation steps. Those are pretty much complete and they're internal, but let's take a look at that second group a bit more: standardize, modernize, and innovate. We all have modern .NET at Unity, and we want to use more of it. So this is really about putting Unity in a position to adopt the latest .NET technologies when they're released. We need to work on building on top of existing .NET solutions instead of forking them. And in doing so, we can get things to Unity users really quickly. And what are the modern .NET technologies on the horizon? Well, let's think about those 3 pillars again. For development workflow, we've got iteration time, use of MS Build, and NuGet to leverage all these great libraries. Now, like JB mentioned, Unity has a package management ecosystem, Unity Package Manager, or UPM. It's going to stick around. We think it can work well with NuGet. They can both coexist, and we're going to talk about how that's going to happen a little bit later. On the .NET Runtime pillar, it's really all about performance, right? How can we bring the best performance and debugging tools to users? Core CLR has got some great base class libraries with great APIs. And finally, for the Unity Runtime, we want to make sure it fits and feels like a modern .NET API. But I want to take a step back for a minute. Let's dream and think about, where could we take the developer experience with Unity in the future? And this is where innovation comes in. I don't know about all of you, but I love writing software. I love making things and being a creator. There's this amazing experience we feel as software developers where the barrier between our imagination and our creation is blurred. We want to make that development experience at Unity a joyful experience. So what does that mean? Well, for the development workflow, it's all about fast iteration, getting that concept to experience really quickly. For the .NET Runtime, we need to make sure we get performance by default. Whatever's the best way to run your code on your target device, Unity should choose that and just do it without any input. And finally, for the Unity Runtime, it comes down to scale. How can we make your real-time 3D content work well on the most low-end mobile phone to the highest console, from your desktop to your cloud server? We don't know what the future will bring as far as platforms, but we know it's going to be different. We've got to be ready to scale to all those different devices. So this is all really ambitious. And that's why, our most important focus area is communication and collaboration, because we need your help to do this. We've already begun to communicate more about our .NET plans on the Unity forums and via blog posts. We're going to talk about those a bit later. Please join us on the Unity forums. We'd love to get more interaction from the .NET community. We've got a great community of Unity users out there right now to help you get started. And we're engaging with the open source community. We're working on pushing more of our changes to upstream .NET repositories, and we're going to continue to do that. Well, that's most of what I got for our high-level strategy, but let's dig into some details now. First, I want to talk about Unity's Burst compiler we use for high-performance C# code. This is some pretty cool tech. Okay, so C# is a large and complex language, right? Lots of use cases, many things we can do with it. But just imagine if we could kind of scope it down to a small subset, a subset that we just need for high-performance coding games, and then we can make assumptions about that subset in the compiler to improve performance. That's exactly what Burst does. We call this subset high performance C sharp or HPC sharp. And what do I mean by subset? What's this actually come down to? Well, first of all, it's really about value types, stack allocation using primitive types, and C sharp control flow. And it's about avoiding things like reference types, classes, GC allocation. Now, by optimizing this subset, we can get performance that's on par or better than native code with the convenience and expressiveness that we love from C sharp. That's really cool. But you might be wondering why we don't use existing tech for this, right? Like we've got Unity's own IL to CPP technology, native AOT is out there. We think that Burst gives us some advantages. First of all, it uses the LLVM compiler infrastructure behind the scenes. And LLVM's got some great optimizations, and especially great optimizations for auto vectorization, right? If we're talking about SIMD code, single instruction, multiple data, modern processors are pretty amazing. And sometimes it's difficult to get our compilers, C# and C++ to take advantage of those processors. With Burst and some really focused optimizations we'll take a look at in a few minutes, we can do that really well. And second, Burst is tightly coupled to Unity. It has deep knowledge of the way Unity works, it has deep knowledge of game development workflows. So things like Unity's data-oriented tech stack, DOTS, or Unity's job system, they work really well with Burst to give us the best code. Let's take a peek at what the Burst compilation pipeline looks like. How does it actually work? Well, on the left there, you can see we've got our .NET assemblies. We use Roslyn, like I mentioned earlier, to produce IL code, .NET assemblies. Then Burst uses the system reflection metadata library to read those assemblies and transition the IL from a stack-based IL, like we normally get in the .NET VM, to a register-based IL. That lines up a little bit better with LLVM's internal representation. So then Burst takes that IL code, the .NET code, and emits LLVM IR. That's the code that LLVM can use for its optimization passes. And then Burst uses those optimization passes. Many of them are existing ones that lots of compilers use. We've got some special ones that we've written just for game development in Unity. And one really cool thing about this is we can do this without forking LLVM. Burst ties into LLVM's existing pass architecture. Now, at the end, we've got native code for your target platform. And then we use hooks in our VMs, Mono, IL to CPP, and Core CLR to run that native code with really no overhead to call right into it. So that's pretty cool. I want to highlight a couple of things we've done in Burst this year. And really, we focused on 3 key areas, but all of them are related to developer happiness. The first one is iteration time. You've got this compiler that can get native code to your device, and it's great code. How do we get it there faster, right? So we've improved our algorithms to detect changes and caching, so we only compile just the smallest amount of code with Burst that we need. Burst debugging is really great now. It's seamlessly integrated with Mono, so you saw JB do some debugging with Unity earlier. You can now do the same thing with Burst, right? A function that's compiled with Burst will work out of the box in the debugger. And finally, if you're using Burst, you probably care about the details. You probably want to look at assembly code. You want to understand at the lowest level, what's my performance like? So we've improved the Burst inspector. We've got better search functions, great tooltips now for the assembly code, and auto scrolling right to your job code. So you can get past all the wrapper code and find the code you really want to look at. Okay, that's enough slides for now. Let's look at a quick demo of the Burst compiler in action. So here I've got a recent version of Unity. This is Unity 2022.2. It's the current beta, and I'm using Burst version 1.8 from the Unity package manager. So if you want to try out Burst, I really encourage you to download the Unity beta and Burst 1.8. This is all available today. We'd love your feedback on some of this stuff. So we'll do a little demo here. If I take a look at our code here, this is kind of the hello world of Burst. It comes right off the Burst documentation. Here we've got the Unity job system. The job system is a native threading system that's exposed through managed code. So it's the power of native performance, but it actually gives us a lot of safety in C#, so we can kind of fearlessly do concurrency. We can schedule a job, it's asynchronous, and here we'll wait for the job to complete in this example. The inputs to the job are these native arrays. This is a contiguous array of 10 floats here for the input and 1 float for the output. This is allocated in the native code, and you see down here we have to call dispose to clean up our native memory. We're going to initialize the array with some data and give it to the job and give it a call. So let's look down here. This is where Burst comes into play. The job runs via this execute method. So you can see we're iterating over the array of inputs. We just sum up the values, put those into a result, and put that into the output. A couple of things I want to call to your attention to here. So first is this Burst compile attribute. This is what kind of kicks things off. This tells Unity, hey, use Burst to compile this C# code. And explicitly, this code is HPC sharp. So if we're using something outside that subset, then Burst is going to go and give us a nice error. And then we've got these read-only and write-only attributes. These help Burst and the job system understand the inputs and outputs to give us better optimizations. So if I flip back over to the Unity editor, I can go to the Burst inspector. And this is where I can actually look at the assembly code. So if I jump in here, I'm looking at my job here. This is the name of the job. And you can see a couple of pretty interesting things. So I've got in yellow, this is my C# code that I was just looking at, right? There's the loop. Here's our sum. But you can see around here, I've also got this assembly code. This is AVX2. So this is Intel 64-bit assembly with the AVX2 instructions that I'm targeting right now. And I don't know about you, but I'm not an expert in assembly. So one of the things I struggle with is kind of how do I look at loops in assembly? And the Burst inspector's got some nice features. So these arrows, right? So for example, I can say, here's my loop, and we're going to have a quick check in assembly to say, is there anything to iterate at all? If not, I'm going to jump way past the loop all the way down here and keep executing. But if there is something to execute, I'm going to go into the loop. And then I'm looking at my assembly instructions. And this one, there's so many assembly instructions in Intel assembly, right? I can never remember what they all do. So we have tooltips here that show us, okay, this is adding, single precision floating point numbers. And that's our sum. That makes sense. V add SS. And as we come down through here, I'm decrementing my loop counter, doing a conditional jump. And look, I can jump back to the top of the loop if I need more to iterate. Otherwise, I fall through. So the Burst inspector is really a great way to see the assembly code you're looking at. And one of the things I really love is, you're probably targeting multiple devices when you're using Unity. So suppose I want to look at what is this on maybe a lower end 32-bit Windows machine with x86 SSE2. I can see my assembly instructions here. Notice the V add SS became an add SS instruction, right? Or you could even look at maybe something on mobile. So let's say I've got, ARM v8, or maybe I've got one of those cool new, Windows ARM 64 dev kits I'm running to. Then, hey, I can check out the ARM assembly. So there's a lot of really cool things we can do with the Burst inspector. But something we've not seen here is auto vectorization. And that's really because this example doesn't lend itself, and Burst can't really do much with it. But let's look at another one. If I switch back to my other example, this is going to be pretty cool. So we'll see how Burst does that SIMD, that single instruction multiple data code. Notice that we're operating at a little bit lower level here. We've got a couple of arrays. I want to point out here that these are stack allocated. So remember, in HPC#, we can't do dynamic memory allocation. So we can't just say new int array. That'll give us GC allocated memory. So we have to allocate these on the stack. And then in real code, we'd have something here that probably initializing with some useful data, but that's not too important for our demo. We're going to pass those right into this sum array values method down below. And as you can see, this method is going to just iterate over the arrays, kind of in lockstep, the arrays together. It's going to take the data from the source array and just sum it up with the data at the destination array at each location. The thing I really want to point out are these no alias attributes. So in the other example we saw, we had native array. And one of the cool things about using native array is it has kind of the alias analysis built in. But with raw pointers, we have to give Burst a few hints. So what does aliasing mean? Well, this integer pointer to destination could point to any location in memory, right? It might point to the same place source is. If that's the case, Burst is going to have some trouble optimizing this loop because it has to make a lot of assumptions. Oh, this memory, if this memory changes, this memory might change then, right? But if we tell it that these two addresses don't alias, meaning they don't point to the same memory or they're totally distinct, then Burst can really go to town on this. So let's jump back over to the Unity editor and see what we get in the Burst inspector. So if I jump to, let's see, the vectorization job here. Okay, here's our stack allocation, right? This is what we saw at the top of that. We're setting it up, but I really want to find where we're doing our SIMD. So one of the things I can never remember is what the assembly instructions are for the SIMD instructions. So if I just use Command F here on Mac, I've got a nice search feature. I know it's going to be something like add. So you can see just like an editor, I'm kind of jumping through my different add instances, and then there it is. I found it. Okay, cool. So here are the assembly instructions we're using are VP add D, right? And of course, yes, this is a SIMD add of packed integers. So it's going to take an array of packed integers and these SIMD registers and add them up multiple operations at a time. So we can see we've got the C# code here, and then we're doing the additions right here. And of course, also I can look at other parts of the code here. Here's the wrapper code, so I can see everything that Burst is compiling, all the code it's going to execute. And then if I want to jump around to different jobs, you can see as I jump to this job I looked at before, we're right back at the job code. Same thing, vectorization, right back at the start of the job code. So Burst is a really cool technology because it gives you the expressiveness and the power of C# with the performance of assembly code. And it mixes in this great debuggability. let's move on and take a look at what we're going to do in the future with C# and .NET. First, I want to talk about that development workflow pillar, right? What's on tap? Well, it really all comes down to standard .NET workflows, right? We're decoupling our compilation pipeline in Unity so we can use the C# compilation in more places. We're going to move to MS Build, an SDK-style C# project with full support for NuGet, like JB mentioned. We realize that Unity's got lots of great options for asset management for things like textures and sound assets, but source code is different. So we're going to decouple source management from other assets in Unity and allow source to be managed more like a regular .NET project. And finally, and probably most importantly, we're looking to really improve that iteration time. You know, as developers, we don't always get things right the first time. We make mistakes. We've got to try things out. So we want to improve that iteration, that flow loop. Now, if you follow us on our forums and our blog posts, we'll be talking about a lot of this in the coming weeks and months, but I want to dig more into the one about MS Build and SDK-style C# projects. So if you're a seasoned Unity developer, you've probably seen an ASM.def file before. If not, just bear with me for a minute. This is kind of an odd thing. This is a JSON file that we use in Unity to describe our build system. So if you've got a collection of C# files and you want to compile them into an assembly, you'd write an ASM.def. The analog in the .NET world is CSproj. Most of us have probably seen that before, right? So in Unity, we're going to automatically transition from ASM.def to CSproj files. And once we're using CSproj files for our build system, then we can do really cool things like add a package reference. We get NuGet support. It'll be integrated directly with Unity. We can also drop down to the .NET CLI that I love to use and use all the great commands there. Now, you might be wondering why we can't just add these features to ASM.def, and realistically, we probably could, but we think that there's a lot of advantages to moving to kind of the common .NET build system. First of all, ASM.def is limited, right? It doesn't support some features of MS Build and C# project right now. And C#, on the other hand, C# project gives us a gateway to the whole MS Build ecosystem, which is really cool. It lets us extend the build system, and a lot of NuGet packages already rely on this feature. And it lets you use C# in other ways. Suppose you're building your game and you want to have tooling around your game and you write C# projects. You can do that directly in Unity with MS Build. That's really great. We get better integration with the .NET ecosystem too. You know, things like Roslyn source generators will integrate nicely in any new features that come out. But really, the most important thing is the compilation performance. Right now, when you compile in your IDE Visual Studio, you have to recompile in Unity because it's two different build systems. And we want to just use one compilation. That'll give us a much better iteration time in the editor. But how do Unity packages fit in here? I've talked a lot about the Unity Package Manager already. Let's go through an example and show how Unity packages and NuGet and MS Build and all this stuff works together. So let's say I've got a game in Unity with some C# files and an ASM.def. That's what you might have right now. Behind the scenes, we're going to do an automatic conversion from that ASM.def into a CSproj. You're free to leave the ASM.def in your game if you want to. It'll still continue to work. But internally, we're going to use CSproj. Now, of course, you'll also be able to write a CSproj in your game. You could create a different assembly with a CSproj. And once you do that, now you get access to NuGet. You can also have a Unity package, and you can author that with an ASM.def or a CSproj. But if you choose CSproj, then you get access to NuGet from Unity packages as well, which is pretty cool. So now I could ship a Unity package that uses something from NuGet. Of course, a Unity package can always reference another Unity package. That's not going to change. Now, here's an important thing I want to point out. We're not going to allow NuGet to reference Unity packages. The two ecosystems have different purposes, right? Unity packages are shipped as source. They can include things besides source code files. We want to make sure that we keep the dependencies lined up in the right direction. So Unity packages will always be able to reference NuGet, but we will not allow NuGet to reference Unity packages. Now, once that's all done, we'll use MS Build to compile everything, right, with the standard .NET tools, whether it's the IDE like Visual Studio or the build system. We'll compile the assemblies, and there we go. We've got game assemblies ready to go to run your game and your amazing content. Okay, let's move on. I'm going to consider our second pillar now and talk about the future of the .NET runtime. What do we have on tap for this? Well, here, it's really about moving Unity from a .NET Framework-based ecosystem to a .NET Core-based ecosystem. Right now, Unity is all based on .NET Framework. But we've got this great .NET Standard API service we could use to bridge that gap. So we can ensure that projects which work in Unity now will continue to work when Unity moves to the new .NET Core ecosystem. To understand how we're going to do this, I want to take a look at Unity's internal architecture. There's a lot on this screen, so just bear with me. Let's start at the bottom. First, it's kind of important to point out that Unity is not really a managed application. It's actually a native application written in C++. It hosts the .NET runtime, and it does that via an embedding API and via runtime invoke callbacks. Now, Unity's also got a lot of managed code. And the engine code, as well as user code, of course, is written in C#. So often, code in Unity is crossing that native managed boundary. And in fact, the .NET runtime does as well. You can see the .NET base class libraries, right? This is where we've got things like string and list and thread, all the things you know and love from the .NET standard library. Unity currently uses Mono's implementation of the standard library, the BCL, and Mono's runtime. In the future, what we're planning to do is swap that out. So the base class libraries will come from Core CLR, and the runtime will come from Core CLR as well. And we can do that because of the .NET Standard API surface. As long as we've got user code and package code and Unity engine assemblies building against .NET Standard, then we can ensure that we can swap those out because both Mono's BCL and Core CLR's BCL implement .NET Standard. So that worked really well. But there's a couple problems here. First of all, this embedding API. Mono has a really rich embedding API. Unity's native code communicates with the .NET runtime on a regular basis. And Core CLR doesn't have that API. So my team at Unity right now is actually implementing the Mono embedding API on top of Core CLR. When that's complete, we're going to push that upstream to the .NET runtime repository, so it's available for everyone. But second, there's direct calls to and from the Unity C# code right into that Unity native code. Now, the native code will call into C# via runtime invoke, and the C# code calls into the C++ via these things called internal calls. And I'm going to talk about those a little bit more in depth. An internal call is a call directly in a function pointer, which uses just a really little bit of marshalling, not nearly as heavyweight as pinvoke, for example. And when that happens, the native code in the C++ side has to know a lot about the C# code, like the layout of objects and some details about the GC. This works great with Unity now, but if we're going to use Core CLR runtime and Core CLR's garbage collector, we're looking to get much better performance from the Core CLR GC, but it comes with more restrictions. So we have to modify the Unity native code to make that happen. So I'm going to talk a little more in depth about what we're doing to solve that problem. The Unity native code right now in the engine makes two really important assumptions. First, it assumes that it knows the layout of managed objects that are allocated on the heap. And second, it assumes that the garbage collector won't move those objects while it's using them. And both those assumptions work for Unity's current garbage collector, but for the Core CLR GC, neither of those assumptions hold. The Core CLR GC gets better performance because it doesn't make these assumptions. So we have to make some changes. How can we do that? Let's take a look at an example. Suppose I've got this class. This is a heap allocated game event with two fields, a float and an object. That's a Unity engine object. That's another heap allocated object. Now, in Unity native code, we probably have something now called a native game event. This is a mirror struct, which kind of has the same layout as the managed code. So when we cross the boundary from managed native code, we pass a pointer to the game event, and we say, oh, it's a native game event. That first field, the float, that works fine. It's a blittable type. It has the same representation in managed native code. But that second field, the object, becomes a pointer. That's a C++ pointer that points directly into the GC allocated heap. For the Core CLR runtime, this doesn't work. Core CLR is going to reorder the fields in managed memory. It puts all the reference type fields first in the managed memory because that gives the GC less memory to scan, which allows it for better performance. So then our native game event is going to be looking at the wrong data, right? How can we solve that problem? Well, we can use standard .NET marshalling techniques, right? We can tell the game event, hey, you need to have a struct layout that's sequential. So Core CLR will give us a representation of game event that will work with the same layout in native code. And then we can make our native game event use a handle instead of a pointer for that object. This will be a GC handle, which means we can ask the GC, hey, we're going to use this data, don't move it. When we're done moving it, we can tell the GC it can move again and go ahead and optimize around it. So how might this look in practice? Well, suppose we've got this on-jump method where we take an actor, from your game, and we're going to call handle sound event whenever the actor jumps. And handle sound event's implemented in Unity's engine code. So right now, handle sound event might look something like this. You see, we've got a raw pointer we're passing to that event. That's heap allocated memory again, right into the GC. And then on that event, we access things directly, these fields directly. We're changing the Unity native engine code to do stuff like this. The event now is going to be a handle. It's a GC handle. And we've got some generated accessors to get access to those fields, the data behind those fields, in a GC safe way. At Unity, we've written a custom marshalling layer that lets us do this by taking advantage of modern .NET marshalling techniques and some things we know about the Unity runtime specifically to give us really great performance as we cross that managed native boundary. So we can do that with good performance and deliver the great performance we get from the .NET Core, the Core CLR GC. Now, if this is something that interests you, I'd really encourage you to check out our Unity blog. We put up a recent post about how we did exactly this for our Unity animation event, which is a really commonly used event in Unity. It goes into some details about how we did optimization and how we made this work in a GC safe way. So it's pretty cool. Okay, I want to take a look now at the roadmap. How are we going to change the .NET runtime in Unity? Well, amazingly, it's already started. In Unity 2021, we shipped the latest Mono technology from the open source Mono repository. In Unity 2022, we updated the engine code. So it worked against .NET Standard 2.1. And currently, my team's at work on the Core CLR player so we can deliver the best .NET experience across platforms like Windows, Linux, and Mac desktop. And then next, we're going to change out Mono as the JIT runtime in the Unity editor and use Core CLR instead. So going forward, we're going to have Core CLR replacing Mono as our JIT runtime. We're going to continue to use IL to CPP as the AOT runtime for those platforms and Burst for high-performance code. Our goal at the end of this roadmap is to release a new version of Unity with .NET right when .NET's available. And so once we make all these transitions, we'll have access to that full .NET API, like .NET 7 or .NET 8, depending on whenever the release comes out. Okay, I want to give a quick tease of something cool about the Core CLR player, and that's mixed mode debugging. So let's do a bit of live coding. All right, so I've got a build of Unity here from one of our testing branches I made locally. This is on Windows, and I'm using a little benchmark project we have, which does an SHA 256 hash. And in the Unity project settings here, I'm using the Core CLR scripting backend. This isn't publicly ready yet, but we'll hope to be bringing it to you really soon. Okay, let's take a look at some of the code here in my project. So in this benchmark project, we've got this update test method that gets called every frame. We create a string here, and then we're going to compute an SHA 256 hash. And my implementation right now is using the .NET BCL to do this. So let me go over here to Unity. We'll build and run the game, just to give you a sense for what it looks like. Kind of one of the cool things about Core CLR, of course, is it's JIT runtime. So we get, a really fast build here with great performance. So when I run this, you'll see lots of numbers scrolling by. These are the hash values that we're computing. Down at the bottom right here is our counter we use for benchmarking. That's not too important right now. The thing I really want to highlight is how we debug this. So JB showed us debugging in Unity already. And what's pretty cool is with the Core CLR runtime, we can do that and more. So here, I've loaded that benchmark executable into Visual Studio 2022. And let me take a quick look at the properties here. If I zoom in, we've got mixed mode debugging enabled here. We're doing mixed mode .NET Core and .NET 5. So this should let us debug native and managed code together. So if I just go ahead and start the debugger, if everything goes well, we're going to run the Unity executable. Remember, it's running a native C++ executable that hosts the Core CLR runtime inside. And we get our great debugging experience in Visual Studio. So you can see down here, I've got, my watches, everything that I expect there. Take a look at the call stack. This is pretty cool. I've got both native and managed code on the call stack. So this is new for Unity. With our existing runtimes, we don't have the ability to do mixed mode debugging. So let's see if I jump into a bit of the Unity engine code. Since I've built Unity locally here, we can see this. Here we're iterating through the systems, right? These are the systems that Unity engine knows about. It's calling the update function, which of course we call here in our benchmarking library and directly into our update test. So let me just go ahead and run this, get to another breakpoint, and let's see. Our return value for the hash code, this is important. Let's see, it is, what is it, 6911. Let's remember that number. Okay, so suppose that I want to use a native library for SHA 256 hashing. Let's go ahead and do that. So I change a bit of code here. Go ahead and write a SHA 256 implementation native. Let's think about what we want to do here. So I probably need a byte array, and we're going to need 32 bytes to do an SHA 256 hash, right? And then I'm going to call a method, SHA 256 native, we'll call it. And I'm going to pass that our input and our result array so it can give us the data back out. And I'll simply return our results. Okay, I need to write a little DL import attribute here so we can hook up with some native code. And I've got a Visual Studio project already set up to compile SHA 256 demo DL as a native allow. And I need to write an extern. So let's do private extern void. And I'm calling it SHA 256. Oh, look at that. Visual Studio is pretty cool. There we go. Let's just change this to result just so I don't get mixed up on my naming. All right. So there's our managed code, which is going to call into a native method. Let's go and implement our native method. So I have another Visual Studio instance set up here with my native code. Here I'm using this pretty cool SHA-256C library. You can check it out here from GitHub. It's available in the public domain, but it's pretty cool if you're interested into how you'd implement this hash library. I'm not going to implement it now. I don't have the skills to do that, but I certainly read some glue code here. We'll try to get that called. So let's see this void. It's important that we get the name the same when we're doing pinvoke, right? SHA-256 native. And that input string is going to become a const char star, right, on the C++ side. And our byte array is going to be a uint 8_t result, and that's going to be 32 bytes. All right, pretty cool. So this library has a nice little calc SHA-256 function I can call. And let's see, the first argument is the result, and then I'm going to have to pass in our input as the second argument. And then the size of the input, we're just going to use friend Sterling. All right. Yes, of course, I need to export this. This is from the DLL, right? So tell the linker to export it, and let's make sure we give the right calling convention. Standard call is going to be the default calling convention for invoke. Okay. So I'm going to go ahead and build this, and I've set up a post-build step, so it'll copy the DLL directly into my Unity project. So if I jump back over to Unity, and you can see here, this is one of the things that we're trying to get rid of is that extra build, right? Pretty soon we'll have the build in the IDE, so when Visual Studio builds my C# project, Unity won't do it again. But I'm going to go ahead and do a clean build in Unity to make sure that native DLL gets copied into the output properly. And then if all goes well, we should be able to debug it directly in Visual Studio just with a quick little F5. We'll have mixed mode debugging going. Let's see what happens. Okay, so I'm going to put a breakpoint in here. All right, call SHA-256 native. There we go. Okay. So we're still in managed code here. Again, we're loading up all the symbols. And as the runtime loads up, we'll come here. Let me go ahead and run. Okay, we're here. And if I just run past this, we get an exception. Okay, let's run one more and see. Unable to find an entry point. Yes. Okay. So this always happens to me when I do pinvoke stuff. Let me go over to the developer command prompt. I'm going to go ahead and use dumpbin to find out what is being exported on my native DLL because I've done something here. So let me go begin to the Unity player build here and find that native DLL. If I do this, what do we get? What are we exporting? Okay. So you can see here, this is the C++ linker name mangling, and that's not what I want. I don't know what that name is, and I can't really easily generate that in C# code. So I'm going to do extern C here. And this will tell the C++ linker, hey, I want C name mangling for this thing. So I'm going to go ahead and build this again. Pop back over to Unity. Let's do a clean build. And then once this builds, anytime I'm doing pinvoke stuff, I always want to kind of double check because it's easy to get wrong. So I'll go back to my Visual Studio developer command prompt and let's run dumpbin one more time just to see if we have the right thing now. Okay. Yes, that looks a lot better. SHA-256 native, that's what I named it. Okay, cool. So if we come over here to our benchmark, okay, let's run this again. And this time, hopefully, we'll get the right hash value. What was that value? Okay, let's run here. We'll run. We got a value. Let's see. Oh, yes, 66911. Perfect. Okay, cool. So we got the right hash value out. Our native library is working. So, one nice thing we can do then is, let's say I want to go to, I've got this compute hash file I had over in the other Visual Studio with my C code. I can put a breakpoint right there. Let's just go ahead and run. And we should be able to step right in this. And I can actually probably just remove my breakpoint over here, right? This isn't really too important anymore. If I go ahead and run, now I'm in the C code. And I can step through my, C++ code, my NIF code, see what's going on, F5, I'm back out. Kind of the full Visual Studio debugging experience, mixed mode debugging, everything I expect, all within this hosted Core CLR runtime. So that's pretty cool. Again, the team's hard at work on the Core CLR player, and we're looking to bring this to you really soon. Okay, but finally, we've got one more pillar. We've talked about the development workflow. We've talked about the .NET runtime. I want to talk about what's on tap for the Unity runtime, because there's some pretty cool stuff you could try out today, actually. So really, we want to make sure that this Unity runtime that's got a lot of great features for real-time 3D content, we want it to work with modern .NET code. Asynchronous programming has been a cornerstone of game development for decades, really. We want to bring the async await tools that are in .NET to Unity. As you saw, Unity is a hybrid engine. We've got native and managed code back and forth, right? We know a lot of games do this. .NET has some great marshalling abilities, some ways to bridge this gap in high-performance ways. We've got great things like Span for expressive and efficient data management. These are all the things that we're looking to bring to the Unity API right now. I want to talk a little more in depth about async await and what we're doing with that. So if you're new to Unity, follow along with me here. If you're an experienced Unity developer, you may have seen this before. This is a start method in Unity, which is kind of how we kick off the method that executes for every behavior. And it returns an IEnumerator. That's a type in Unity that gets used for coroutines. So you can see there about the third or fourth line down, there's a yield return null. That means, hey, when we hit this statement, go ahead and yield control back to the game engine and call me back after that statement on the next frame. So it's an async processing, which is pretty cool. It works well. But if you're new to Unity, if you know .NET async await, this is a little different, right? It's not the same. It's hard to cancel things when you're in coroutines. So let's imagine that we could make start an async method. This is something that probably most .NET developers recognize now, right? In Unity, we've introduced this new await compatible or async await compatible type called awaitable. It's really optimized for Unity. It uses dynamic memory allocations that are pooled behind the scenes. It fits with the Unity threading model by default. Awaitable is both await compatible and it's usable as an async method return type. And every yield returnable object has an awaitable equivalent. See that next frame async method there on about the third line? Every async operation is also awaitable. And common object in Unity will now have this cancellation token property to help you handle cancellation. So, when you exit play mode in Unity or you want to destroy a game object in your game, if there's an outstanding async task, we can cancel that. And I'm really excited about these changes because we've just shipped these literally in the past week or so. If you check out the Unity 23.1 alpha, you can get access to these. There's been a lot of discussion on the Unity forums already about, what the naming should be, what the feel of this code is, how can we make it work with existing libraries that use async await with .NET. So I want to really encourage you, try out Unity, grab our latest alpha, and check out some of these async await things. Give us some feedback because we're really kind of shaping the future of what Unity coroutines and async await programming in Unity is going to be. Okay, so there's a lot of changes coming here. We've talked about a lot of things changing in Unity. If you've got an existing Unity project out there, or you're tinkering, or you want to start with Unity, what can you do to kind of be prepared and make sure that you're ready to transition all of your great real-time 3D content to this new .NET world? Well, there's kind of two things we recommend. The first is use the .NET Standard API. Like we saw, that's going to bridge the gap from the mono base class libraries to the Core CLR ones, give us access to a lot of new APIs. So make sure you use that. And then second, we've seen the Core CLR GC gives us great performance benefits, but it comes with some more requirements. So just use modern, safe C# coding practices, right? The things we know and love. Avoid access to things like managed object pointers directly. If you do that, you'll be ready to kind of transition with us at Unity to this new .NET world and open up kind of an amazing world of tools and performance. The story of .NET Unity, we had that slide at the beginning. It's like 15, 20 years long, but really, I feel like it's just beginning. What have we taken a look at so far? What have we taken a look at today? Well, man, so much, right? We've made developer happiness in Burst this year, and Unity 2022.2 beta and Burst 1.8. It's available now. Please go check it out. I'd love to see what you can create with Burst. We've got these new async await tools, right? They're available now in Unity 23.1 alpha. Again, we're looking for feedback on those. We want to kind of shape the future of that API. So help us out there. For MS Build and NuGet, there's that whole world out there. We want access to it. We're working on that at the moment. We don't have a release date, but we'll hopefully have it out soon. And that Core CLR JIT is just amazing for performance, for debugging. I'm really looking forward to getting that into all your hands. Well, for me and, for many people, gratitude is really important. So, I want to take a moment to say thank you from all of us that work on the .NET Tech Group at Unity. We love working with our users, whether you're an experienced Unity developer or you're new to Unity, you just want to get started. Thank you for coming along on this journey with .NET with us. Thank you for using Unity, and thank you for pushing us to make Unity better. We want to connect with you. You can find me on Twitter. Join us in the forums. Like I said, we've got a great community of developers, especially this experimental scripting previews. That's where a lot of the people in the .NET Tech Group hang out on the Unity forums. We're there to answer questions. We're there to take feedback. We'd love to have you join our discussion. At Unity, we truly believe the world is a better place with more creators in it. And we want you to come along with us on this journey of creation in the future. So thank you.
There's a mute button, and I didn't hit the mute button. Thank you, Josh, for dealing with me forgetting to hit the mute button.
No worries, I've done the same myself many times.
I love seeing how the Unity product is upgrading from .NET Framework to .NET Core. We're going to get modern development in there, modern capabilities, new versions of C# support in there. That is awesome stuff, and the great new technology that folks are going to be able to use in building games. That's got to be great for everybody.
Yeah, like I said, we're really looking forward to delivering some of this. Some of it's already out there. I'm constantly amazed by the things people create. I see some of these games are made with Unity, and wow.
Yeah. Oh my goodness. You're absolutely right. Well, thank you so much for joining us as part of .NET Conf. If folks have some questions, of course, reach out to Josh there. You see his Twitter on screen. Yeah. And we'll have this video all wrapped up, edited, and on the YouTube channel early next week. All right. Thank you so much, Josh.
Well, you're welcome. Thank you for having me. It's been a great time.